Hey there, in this video I want to talk about how we can use the shooting method to find eigenvalues for differential equations, specifically for differential equations that are linear and homogeneous. So I've typed up an example of such an equation. So linear meaning we're not mixing the x's, the derivatives of x, with each other. So like if I had an x dx dt term, that would not be a linear equation. And homogeneous means right hand side is 0, or at least we could write it that way. Such equations have eigenvalues and solutions that go along with those eigenvalues called eigenfunctions. And this comes up most commonly in physics in the context of quantum mechanics. So I've typed up a sort of example to get us going here. So we'll do the example of the Schrödinger equation in the case of the infinite square well. We'll give it some width, and we'll go the simplest potential we can, v equals 0, which then turns the Schrödinger equation into this pretty simple looking differential equation, which is an eigenvalue problem. You can even see the way it's written makes it scream out eigenvalue problem. On the left-hand side, we have an operator, second derivative acting on psi, gives you the same psi back, but then multiplied by some constant called the eigenvalue. And what I want to do is figure out what values can E have, with the physical manifestation of this being what is the possible energy levels in the infinite square well. Okay, and so we can do this with a variation of the shooting method. So basically we're going to try different starting values until we get the result we want. Although by starting value, I don't mean psi and its derivative. By starting value, I mean different values for E. So let's just start coding it up to see what I mean here. So I'm going to start with defining some constants. The width of the square well L is going to be 10. I need some initial conditions here. So we're going to do psi initial equals 0. That would be the boundary of the square well. We also know that psi final has to be 0, and that's how we can use a shooting method to get a solution. Basically, we're going to try values until psi final equals 0. So let's just remind ourselves of that, although it's not something I put into the code directly, because the way we're doing here with solve IVP is we need to have starting conditions. Well, if you are wondering, there is a SciPy solve _BVP for boundary value problem, which you might think would do this for you, and it does, but it is just absolutely a nightmare to try to use this function. It doesn't really follow the same kind of conventions as some other SciPy functions. So it's there's documentation for it. It's just too painful. So anyway, in my experience, it's a lot easier just to do it the way I'm showing you. Anyway, got a little sidetracked there, yelling at SciPy and the way they wrote it. So we have to have another starting condition here, which is the derivative of psi. Now, here you might think like this is the thing we'd be playing around with. But as it so happens with wave functions, and the problem we're trying to solve, it doesn't matter what you pick for d psi. If E is not an eigenvalue, it just does not work. It's really E that sets the solution. And the way in quantum mechanics we handle the slope is through something called normalization. Like we say that the area under the curve is guaranteed to be 1. So we just need to make up something here, and then we're going to effectively change the value when we normalize anyway. Now we have to be careful. We don't want to start with psi 0 and d psi being 0, because that would be a flat wave function that doesn't do anything. We need something non-zero, so that when we scale it, we still have some non-zero result. So this is arbitrary as long as it's non-zero. And that's okay because we'll normalize later. Okay, so with that, we can now make something that looks a lot like the shooting method. So we're going to basically write a differential equation solver that is itself a function of a variable, and that variable is going to be E. So the differential equation that's being solved here is going to depend on a variable E here. And so the basic workflow here is I want to unpack Y here, which is actually going to be an array of values. In other videos, I've called this thing R. I'm going to call it Y this time for no especially good reason. It is what the SciPy documentation likes to use for its example variable. So since I don't have a good reason not to use Y, I'll use it here. And then what we want to do is return, I don't know why that, well, there's something weird with my indentation. Got an extra space in there. Okay, anyway, then I want to return the derivative of psi, which is by definition d psi, and the derivative of d psi, which is the right-hand side of this equation here. So negative e times psi. Okay, and then I want to write a function that gives me psi final. Actually, let's call it psi L, because final sort of implies time, but really I mean psi at the other end of the square well has to be 0. So psi L here is a function of E, and the idea here is we're going to do some stuff, and then after we do that stuff, we're going to return the, well, psi at location L, so it'll be the last thing in our solution. And then our solution itself is going to come from integrate.solve IVP. Okay, we want to give it our function. We want to give it the range of values we're checking, so that would be 0 to L. We want to give it the initial conditions, which would be psi initial and d psi initial. And then our results are going to be psi and d psi, and they're going to be living in the solution's y attribute here. Okay, now this won't work because f here, like if we look at the way this thing works, it's expecting f to have 2 arguments. And f doesn't have 2 arguments, it has 3 arguments. And that's because we wanted this thing to be a function of e. So how do I let f know what value of e I want to use? Most methods in SciPy have an extra argument here called arg or args, except for solve IVP. And this is actually a issue on SciPy's GitHub. They're going to eventually add it in SciPy 14, I think, which is at the time of recording not out yet, and I don't know when it would be out. So this doesn't exist yet, but normally that's how you would do it. So instead, the way you need to do this is to basically make a new function f here. And so we could go in here and we could define some kind of new f, but actually this would be a great place to use a lambda function because we can just do it all in line. So we're going to have some lambda function that's a function of t and y because that's what solve IVP wants to use. And what it does is it calls f using t, y, and e. And this is going to work because the e here is the same e that was passed into the function that I'm writing. Okay, so now with all of this, we'll be good to go. I want to make a plot of this to get to inspect and see where the energies are. This is a case where we will have multiple solutions. And so since I'm trying to plot something complicated looking, I want to vectorize it. And then we can make some values to test. So a little bit of trial and error at this next step here. So we'll go values from 0 to 1, and we'll do 200 steps just to make a nice high resolution graph. Why am I only going up to 1? Because I've done this before and I know where to look, but in general you would just, you try different values until you found something looking good. So anyway, we're going to plot E and we're going to plot psi underscore L of E. We're looking for places where this line crosses 0. So to help us spot those values more accurately, we'll draw a grid. We'll draw a horizontal line as well, just to emphasize where that 0 actually is. I'd like my horizontal line to be black instead of, it probably would default to like blue or orange, which is, I don't think, very nice looking. Okay, and then we'll show it. So let's see if the code here actually works or if I have to do some debugging. Oh, hey, it looks like it worked. And so we got a plot now. This is the ending psi as a function of energy. And the only allowed solutions have the ending psi equal to 0. And we can see that happens here within this range at 3 points. It looks like at 0.1, pretty close to 0.4, and about 0.9, a little shy of 0.9. Okay, so now let's use a root finder like optimize.newton to get more accurate values for those allowed solutions. So we got solutions near 0.1, 0.4, and 0.9. So what I'm going to do is I'm going to make an empty list to store my results. And then I'm going to go through my list of guesses. And so that's going to be 0.1, 0.4, 0.9. And then for each guess, I want to optimize. So we'll do optimize.newton, calling psi L and looking near our guess. And then, assuming that this actually works and gives us a solution, we will append those into the list energy and print them. Okay, that should work. Yeah, so that's going to print 3 numbers for us. And around 0.1, around 0.4, and around 0.9. Okay, so looking good. And so if that's all you wanted, you could say problem solved. But let's say we now want to know what are the eigenfunctions that go with these eigenvalues. So in other words, what are the wave functions that are allowed? And eigenfunctions. I'm combining the idea of wave functions and eigenfunctions. All right, so if we think about what we want to do here, I want some x values to be the x-axis of my graph. So I can get those with a Lin space. We know we need to be 0 to L to represent the square well, and let's just do 100 of them. And then I've got 3 of these energies, so I think this is a good place to use a for loop. So it would be like for E in energy. For each of those, what I want to do is I want to solve my differential equation and plot it. So we'll do integrate solve IVP. Remember, like we had to do before. In fact, we could just copy our code right here. So we need to use a lambda here because we have to feed E into F. Okay, so we want to solve our differential equation. We're going to get a nice psi here that we could plot. We also get d psi if you cared to plot it. We do have to make a little bit of a change here. This will only evaluate at a few points, so it won't look very good. We want to use the optional argument t-eval to say I want to evaluate at more points, and those points are x. So yeah, even though they're x's, the argument's still t-eval, because that's just its generic name. Okay, and then once we've done that, we can now make a plot. So we'll plot x and psi, and if you were being careful and making very pretty results, we'd add a label at this point so we knew which was which. But right now I just want to get a rough sense of what do they look like. So I think I will do a horizontal line though, just to check if they're symmetric around that. We expect something like that. And we'll do a plot.xlim 0 to L. And here I was saying I didn't want to make it fancy, and then I go and I add code to make it fancy. I can't help myself. What can I say? So here we go. Here is our wave functions. And so this is our ground state energy function. The orange would be our first excited state and second excited state. And if you've had quantum before or modern physics, this should look very familiar to you. Except that these curves are not normalized. You can see that this blue curve has much more area underneath it than the others. And so when we normalize in quantum mechanics, what we're really doing there is we're taking care of the fact that we never really set the initial condition for the slope of psi. And we need some kind of way to do that, some kind of convention we're going to follow. So normalizing in quantum mechanics takes the form, let's just write a little markdown cell here, where you take the integral of the absolute value squared, so go with like a big absolute value here, of psi of x, and then we want another big absolute value sign. We want to square it. Let's add a little bit of space, dx, and that's equal to 1. Just check if that renders. Yeah, okay, so that's our normalization condition. So because in general psi could be complex. It's real in this case though. So we're going to take the absolute value, square it, and set that equal to 1. The way we would actually normalize then is, that means that psi needs to be divided by this integration here, or by the square root of this integration here. So let's take our code here that drew stuff for us, and we need to make a change, which is we just have to normalize psi. So instead of plotting psi, we plot psi divided by our normalization factor, or we could redefine psi to have that normalization already in there, depending on what you want to do with it. And the way we calculate that normalization is by integrating, or carrying out this integration here, and then dividing by the square root of it. So our normalization factor is the square root of the integral. And the thing we are integrating is, we're going to use Simpson's rule here. The thing we're integrating is psi squared well, really absolute value of psi squared. But if it's real, then psi squared is the same thing as the absolute value of psi squared. Okay, and why Simpson's rule is, the reason I'm doing that is because psi is an array. And if I want to integrate an array, I use something like trapezoid rule or Simpson's rule. It's pretty smooth, so Simpson's rule will give us a more accurate result. Okay, everything else here should be the same, so that when I plot, the only thing I've done is I've adjusted psi by its normalization factor. And so now these curves are all normalized and will look a little bit more like what you would see in a quantum textbook. You'll also notice that each of these has a different slope at the beginning. And so in effect, what our normalization factor has done is it's changed the original slope of psi for each of these graphs to guarantee that we're following some kind of convention.